Welcome to Demystifying Math. In this lesson, we're going to be discussing ellipses. The geometric definition of an ellipse is a set of all points in a plane, the sum of whose distances from two foci is constant. Let's take a look at this. Okay, so here we have point P, which will be a point on the ellipse. We also have two focal points, F1 and F2. The center of the ellipse is halfway in between the two focal points. I've also drawn a point P2, which is a reflection of P1 over the line that connects the focal points. Now what I'm going to do is move point P so that the lengths of R1 and R2, the sum of those lengths, is going to stay the same. Notice that the lengths of R1 and R2 add together to give me 10. And no matter at what point I am on the ellipse. And notice that as I do that, R1 is getting longer, R2 is getting shorter, and it's tracing out the curve of an ellipse. Now the P2 is just a reflection of P1 over the line of symmetry of the ellipse. As you can see how this is still always R1 and R2 add together to give me 10 no matter what. And when we do that, we get an ellipse traced out. Okay, so there are actually two lines of symmetry for an ellipse. There's what we call a major axis, which is a longer line of symmetry for the ellipse, and that one goes through the center as well as the focal points. And the endpoints of the major axis are the vertices. We also have a minor axis, which is perpendicular to the major axis. The minor axis is just shorter than the major axis. It also goes through the center, and its endpoints are sometimes also called vertices. The 4 points at the end of the major and minor axis will help us determine the ellipse and find the equation for the ellipse. Now the equation for ellipse is very similar to that of a circle. With a circle, normally we have this equation, which is x minus h squared plus y minus k squared, and normally you have an r squared over here. What I did was just divided everything by r squared. Now, the reason that these r's are exactly the same underneath the x term and the y term is because all the diameters or lines of symmetry for a circle are all the same length. But with an ellipse, the lines of symmetry have different lengths. So the adjustment that we're going to make here is to put two different numbers under each term. One representing length of the horizontal major axis and one that helps us find the length of the major axis or the minor axis. Now this equation is when we have a horizontal major axis, so A is going to be our greater value and B is going to be smaller. Now note that just like with the circle equation, we have the length of the radius underneath each one, which is half the length of the line of symmetry or the diameter. In this case, for the ellipse, we're going to do half the length of the major axis and half the length of the minor axis. And just like with the circle, HK is going to be the center of the ellipse. Now, if we turn it around and we have a vertical major axis that's longer, then the bigger number is just going to be under the y value. Okay, we want to give an equation for an ellipse that has a center at 2, 4. It has a horizontal major axis, and that length is 12. And it has a minor axis of a length of 6. Remember that A is going to be half the length of the major axis, and B is half the length of the minor axis. So when we're plugging into our equation, we need our center, which is at 2, 4. So that's going to give us our h and k values. And then we also need our a and b values. So since our major axis has a length of 12, a is half of that, or 6, and b is half of 6, which is 3. So we get this equation here, and we're just going to square the denominators. Now what we want to do is expand all this out. So we have x minus 2 squared, which we're going to expand as x squared minus 4x plus 4. And we have y minus 4 squared, which becomes y squared minus 8y plus 16. Now what we want to do is clear fractions. So I'm going to multiply every term by 36 times 9. So the first term is going to end up with the 36 canceling. So we're just going to multiply the numerator by 9. And for the second term, we're going to end up multiplying the numerator by 36, and then we have 324 on the other side. So all I did here was distribute the 9 and the 36. And then I brought all the constants together and set it equal to 0. So we have this equation in standard form where A is 9, C is 36, D is negative 36, E is negative 288, and F is positive 288. Notice that A and C are not equal, but they do have the same sign. So if their product is always positive, then you know that that equation is going to represent an ellipse. Okay, we want to graph the ellipse, so we're going to start by finding the center, which is at 2, 4. Then our A value is 6 and our B value is 3. And we want to be able to find 4 points on the ellipse. So we want to actually find the 4 endpoints of the major and minor axes. So if we add the A value to the x coordinate, we get 8, 4. And if we subtract it from the x value, we're going to get negative 4, 4. Then if we take the B value and we add it to the y coordinate, we get 2, 7. And if we subtract it from the y coordinate, we get 2, 1. So these are the 4 points that we found, and I also plotted the center. Remember, the center is not actually a solution to our equation, but it does help us to find the endpoints of the major and minor axes. Now once you've done that, then all you have to do is connect the 4 points with a smooth curve. So you have your ellipse. The formula to find the foci is a squared minus b squared equals c squared, where c is the distance from the center to the focal point. The foci are always going to be on the major axis. Okay, so in this case A is 6 and B is 3. So we're going to plug that into our equation of a squared minus b squared equals c squared. And we get c squared is 27, or plus or minus 3 square roots of 3. So we're going to add it and subtract it to our x value since we have a horizontal major axis. And then we estimated it. So we went ahead and plot the focal points. Remember, your focal points are always going to be on the inside curve of your graph. Okay. A circle and an ellipse are very closely related. They're related by their eccentricity. Remember that eccentricity is going to be c over a, where c is the distance from the center to the focus, and a is the distance from the center to a vertex. And we're referring to a vertex at the endpoint of a major axis. Okay, so we said that eccentricity is c over a. And we also said that c squared equals a squared minus b squared. So in this formula up here, the numerator is actually representing c, which is the distance from the center to the focal point. So here's our center, and here's our focal point. And then your denominator is a, which is the distance from the center to a vertex. And notice at this point where this ellipse is, how it's drawn, your e, or your eccentricity, is almost 1 because the focal point is very close to the vertex, so those two distances are almost the same. Now what we want to do is change this a little bit. So I'm going to bring my focal point in toward the center and look to see what happens to the eccentricity of the ellipse. Now notice that when it was stretched out pretty far, it was almost 1. It's getting smaller and smaller as the two focal points are coming closer together. And also what's happening is our ellipse looks almost like a circle. So it's going to be more circular when your eccentricity is smaller and more elongated when your eccentricity is closer to 1. But notice that with an ellipse, it's never going to be greater than 1. Because your focal point always have to be on the inside of the curve, and in order for it to be greater than 1, your focal point would have to be outside your curve. Okay, so when your graph is more circular, your eccentricity is closer to 0, but still between 0 and 1. And when it's more elongated, your eccentricity is between 0 and 1, but closer to 1. Okay, thank you for tuning in to Demystifying Math.